A2 further maths, complex numbers, exponential form. So last year we started looking at some Maclaurin series and did a little bit of work on them. And the three of the Maclaurin series we looked at was find out what sine x was. And you get these in your formula books, you don't need to learn them. And sine x looked like this. So it's a power series as for different values of x cubed over 3 factorial and so on. And we started doing some work on those last year. And we will do some further work on them later on this year. We also looked at cos x as well, and that was 1 minus x squared over 2 factorial. It was, if you notice, it was very similar to the previous one, except it was the even terms and that was the odd terms. But we also looked at the exponential as well, and the exponential function looked like that: 1 plus x squared over 2. In fact, all three of them were very, very similar power series. What I'd like you to do is just work out what cos x plus sine x is. Okay, so you might want to just do that in your head. Just pause if you want some more time. Okay, so it wasn't difficult, but as long as you're writing it in order of their power, so 1 plus x minus x squared over 2 minus x cubed 3 factorial, then it's plus that, and so on, then you end up with this series here. Okay, now what's important to notice is that series just there is really similar to this series just here. These two are really, really close to each other, almost identical. The reason why they're not identical is the fact that this is 1 plus x, great, that's the same as that 1 plus x, but then we've got minus and a minus there, and we had a plus plus. So we cannot say that these two are identical because they're not, because of the difference in the signs. But we've seen this pattern of plus plus minus minus plus plus minus minus before, and where you've seen that is with complex numbers. Now if you think about this series here, and you think about the what these actually look like if we worked them out as in terms of I, we get 1, then I, then minus 1, then minus I, 1I, minus 1, and so on. What's important about this is you notice that the signs are plus plus, minus minus, plus plus, minus minus. So if I could somehow put these two things together, this and this, then hopefully we should be able to get down to something like this one here. Okay, so let's just have a play and see if we can sort that. So there's our cos x plus sine x series. If I look at e to the ix, in other words, I just directly compare or directly put in that I as a power. Look what happens. Everywhere I had an x before, I'm putting in ix. So ix there, ix squared, ix cubed, ix to the power 4, and so on. Okay? And if I put those all in and then simplify it, what I end up with is a situation where I get 1 plus ix minus that, plus that, plus that. Now those two are really similar. But now we've got a bit of a problem. And the problem we've got is that although we've sorted out the signs, now these terms here aren't the same because they have an extra I in front of them. But what's quite nice is that these that have got the I in front of them were all from the sine x term. Every single one of those came from the sine x. So if I can now change this about a little bit, then we can say that these two are the same. So for example, sine x there is the same as ix cubed over 3 factorial, ix to the power 7 over 7 factorial, and so on. Now why that's handy is now if I can put that instead of this one, then those two should be absolutely identical. E to the ix is exactly the same as cos x plus I sine x. And those two are absolutely identical. Right, so a complex, grab your notebooks then please. A complex number we knew from year 1 can be written as z equals a real part plus some amount of an imaginary part. Okay, and we can plot that, no problem. We also looked at changing it to a modulus argument. In other words, how far do I turn? How far do I need to go to get to that complex number? But what we can do now is we can write a third form, a different form, an exponential form. because we've just looked at this part just here, cos theta plus I sine theta, and we just showed that that was the same as e to the ix, we can now say a complex number can be written in exponential form. Z equals re to the I theta. And all three of those are different forms of writing a complex number. Right, so what I'd like you to do, please, is I'd like you to figure out that table. So you need to figure out things like the R value and then write it in exponential form. You might figure out the theta value, fill it in exponential or modulus argument form. Could you have a go at just flicking between those three different forms and just make sure you're comfortable writing each of them? If you want some help, I can show you the first one. If not, just go and have a go yourselves. Okay, right, pause when you need to. Okay, so if you needed the first example, what I would do for this one, I would definitely notice that I've got a modulus of 3 and an argument of pi over 3. So that means the exponential form is really easy because it would just be 3e to the pi over 3i. The Cartesian form, I'll get my calculator and I'll type in 3 cos pi over 3 equals, that's the real part, 3 sine pi over 3 equals, that's my imaginary part. So I get that for my Cartesian. 3 cos pi over 3 is 3 over 2. 3 sine pi over 3 is 3 root 3 over 2. For the exponential form, I just put the 3 and the pi over 3 in those two places. Okay, right, so if you want to pause and have a go at the others yourself, you can do. Okay, so let's see how far you got. With this one then, you've got to consider whereabouts these things lie on an Argand diagram so you don't make any silly mistakes with your modulus and argument. It doesn't matter whether you use 0 to 2 pi or pi to minus pi for your argument value. I've used up to minus pi, hence my minus 1.03. I also, obviously, you don't need to be exact. Once you've got those two numbers though, you've got your r, you've got your theta, your exponential form can just be written. These two, very, very similar because they both contain r and theta. Right, think about the position of this. You're going back to up 7, so I'm thinking it's going to go around to about 1.85. 7 squared plus 2 squared square rooted, 7.28. So that's going to give me that in exponential form. This is more interesting because it goes minus 4 and minus 3. So I need to be very careful whereabouts I put my arguments. It's going to be minus somewhere between 0 and pi. So minus 2.5 sounds good. 5, 3 squared, 4 squared, square root is 5. Therefore, my exponential form is 5e to the minus 2.5i. This one is the other way around. So I notice I've got an r value of 3, an r value of 8, a theta value of 3. So therefore, I could write my modulus argument form as 8 cos 3 I sine 3. And this one I can work out from here. So done with it the other way around, but it doesn't matter. So 8 cos 3 gets me that, and 8 sine 3 gets me that one. Okay, so well done if you managed to work those out. You need to be confident flicking between each of these three different forms of a complex number. Okay, so something else for you to have a go at. Given that Z1 equals 4e to the 3i and Z2 equals 3e to the 2i, see if you can work out those four things and then express them in the form a plus bi. Okay, so have a go at them any way you like. Pause it there, have a go. Don't just cheat and wait for me. Okay, so let's see what you did. If you converted them to a plus bi form first and then work these out, that's fine. There's nothing wrong with it. But if you didn't, if you tried doing it from exponential form and work these out, you would have an easier time. Because if you look at this here, z1 times z2, I would be timesing those two together. Now what's quite nice about this is because they're exponentials, because they're powers, I could just use my raws or indices. So 4 times 3 is going to get me 12, 3i plus 2i, 5i. And then once it's in that form, I can do 12 cos 5 for one part of it and 12 sine 5 for the other part, and that's going to give me the answer. Okay. What about this one? Z1 over Z2. Again, if you keep it in exponential form, you could just use your laws of indices. 4 divided by 3 is 4/3. That take away that is going to get me just e to the I. So that's where that comes from. And now, again, I've got an argument of 1. I've got an R value of 4/3. I can work out the A plus BI by doing 4/3 cos 1 and 4/3 sine 1. And there we go. That's where that answer comes from. What about if I'm cubing it? Well, if I'm cubing it, again, if you expanded them first, so you changed Z1 into that form and then did to the power 3, you're going to have a lot more hard work than if you had exponential form. Because in exponential form, the laws of indices say you just multiply those two powers. So really, be careful. Don't forget it's 4 cubed as well. We've got 4 cubed is 64. E to the 3i cubed is going to be e to the 9i. And then I can do the same again. 64 cos 9, 64 sine 9 gets me those two answers there. Okay, so very well done if you managed to get those. Finally, a bit of a mixture. Okay, so I'd work this one out first. And then once you've done that, then you can't add exponentials. So at this stage, unlike these previous ones where you can use your laws of indices, at this stage, once I've figured this part out, I'm sort of stuck then. I need to work them both out into A plus BI form and then I can add them together. So in this case, I've got 4 cos 3 and 4 sine 3. Here I've got 9 cos 4 and 9 sine 4. I can work out both of those separately, which is what I've done there, and then I'm in a position to add those together. So well done if you got minus 9.84 and minus 6.25 in the imaginary parts. Okay, so what I'd like you to do, just have a go at expressing both of those. Again, pause, have a think how you do it, and when you're ready, you can have a look at my solutions. Okay, so I want to express both of those. Now, unlike before, without having nice powers in there, nice easy arguments, you can't really do anything because 2 minus 3 is 3i isn't something you can read off an argument very easily. But if I can use my laws of indices and separate these things out, then what I'm trying to get to is a situation where I have a number on the front and then I have a number in front of I here. Because once I've done that, I've now got a number on the front, which is going to be my R value, and the number in front of I, which is my theta value. So that's what I've done. E to the 2 is just a number. So that's my R value. And minus 3 is my theta value. So I have e to the 2 cos minus 3. That's where that one comes from. And e to the 2 sine minus 3. That's what that one is. And don't forget to put the I after it. What about this? Well, more interesting with this, I need to get an exponential in there. And the only way you're going to get an exponential is if you use this trick we've seen before. Okay, so you've seen this before, a similar sort of trick when you did differentiation of exponentials. So what can I do? Well, I can write it with e and ln, and that the reason for that is because then you have the exponential which we need to be able to have it in exponential form. Okay, so what do I do then? Well, once I've written this, and of course e ln 5 is just number 5, I can change that and that using laws of indices and times those two together. So I get this, bringing the 4 to the front. Notice I can just take the I out. And then once I've got that, I now have an R value of 1 and a theta value of 4 ln 5. So I can just type in 1 cos 4 ln 5 and 1 times sine 4 ln 5 I. Okay, very well done if you managed to get both of those. What I would like you to do, just before I give you some more questions to look at, is just have a quick investigation of the relationship between e to the I theta and e to the minus I theta. So if you have a go at just writing both of those out and see what you notice. Okay, if you did work out both of them out, you'll notice that e to the I theta we know is cos theta plus I sine theta. We also know that e to the minus I theta is going to be cos of minus theta plus I of minus theta. Now we did this recently and we looked at how we can change a minus and a cos of a minus and sine of a minus. And we know that cos of minus theta is exactly the same as cos theta. We also know that sine of minus theta is exactly the same as minus I sine theta, okay, because of the reflection situation, okay. You reflect the cos graph, it lands on top of itself. If you reflect the sine graph, you end up with a minus sine graph, it goes underneath. Right, why does that help us? Well, we can see that e to the I theta is a complex conjugate. All right, the reason for that is because if you look, they're both exactly the same, except there's a change of sign on the I part. It's also exactly the same as z and 1 over z, which is what we looked at in a previous lesson. Why does that help? Well, if I try adding those two together, I'm going to get 2 cos theta. Put those together. And if I try taking them away, I'm going to get that take away that minus this gets me 2I sine theta, because we've got minus and minus make a plus. That's quite handy to be able to work those out, because it does lead to some general forms of how we can write cos theta and sine theta. We can write cos theta and sine theta in terms of exponentials using this fact. Cos theta is that, because that is equal to 2 cos theta. Also, sine theta is equal to that because we knew that when we took it away was minus 2i sine theta. So therefore we can write that. Okay, grab both of those on your notebooks. You're expected to know them and you're expected to know how to use them. Okay, so have a go at the exercises on 1b and 2c. So there's some tough questions in there, so don't just skip them. Make sure you have a go at all those, and when you're ready to move on, we can move on. Okay, so we're going to look at a couple of examples on how you could potentially use Demoivre's theorem to solve some more complicated questions. So the first one we're going to look at is using the sum to infinity. So I'll just give you an opportunity to write down the question, then we'll have a look at how you go about answering this question. So find the sum to infinity of the geometric series, and then hence find the answer to that summation in terms of sine theta and cos theta. So just pause there if you need some time to either copy it down or you want to have a go yourself, and then we'll have a look at the solution. Okay, so the first thing you want to look at is the fact it's a geometric series, and that means if it is a geometric series, it should have a first term and then a common ratio, what you're multiplying by each time. And that's the first thing you should try figuring out. So in this case, the first term is just number 1, so we can certainly write down a equaling 1, and the common ratio is what you're multiplying by each time. So it's very easy. If this is definitely a common ratio to get from 1 to 1/5 e to the I theta, then the R value should be 1/5 e to the I theta. Just to confirm that's true on the second one, if I multiply by 1/5 e to the I theta again, I would get 1 over 25, which is great, but I also get e to the I theta squared. But as we know, with the laws of indices, e to the I theta squared is the same as e to the 2I theta, and so on as you go along. So the R value is definitely 1/5 e to the I theta. Now it's asking for the sum to infinity. Now the sum to infinity is in your formula books, and the sum to infinity for geometric series is a over 1 minus r. Okay, now the only reason that works, or the only time that works, is if the common ratio is between 1 and minus 1. So it's important to make sure that when you look at this, is the magnitude of the R value, is the size of the R value going to be between 1 and minus 1? So that's what this is talking about here. Now 1/5 e to the I theta is a complex number. So its magnitude basically working out its modulus, working out its value. And when we look at the size of that, then we can see that that is going to be the same size, the magnitude of it, as we know, that's the R value, that's just the argument. So the magnitude of it is 1/5. Now 1/5 is fine because it's between 1 and minus 1. So if we're ever looking at these situations, it's the number on the front is the magnitude of it, is the R value. Okay, is a modulus. So now we've got that back out of the way, we know we're allowed to work out the sum to infinity. So we could just use that very simple formula, a over 1 minus r, and we should get 1 over 1 minus 1/5 e to the I theta. Now if we're going to neaten this up, what I could do is, to get rid of that fifth there, I could multiply everything by 5. I'm allowed to do that because we're multiplying just numerator and denominator by 5. So I end up with this, 5 over 5 minus e to the I theta. Okay. Right. So I've worked out the sum to infinity. Let's see how that's going to help me answer this next question. Now, instead of going straight to this one, what I'm going to look at is just what is this series? What is this series? How do I write this series? And I've noticed that I could write it like this, starting with k equaling 0, because then you've got 5 to the power 0 is just going to be 1. You've got k to the power e to the power 0 is going to be 1, so that's definitely going to be 1 to start with. And then if k equals 1, I notice it's a fifth e to the I theta. So basically what I've done is I've written that geometric series as series notation. And then the examiner is asking us to look at, hence evaluate this part. Now, if you're going to evaluate that part, this bit just here will help you do that, because we know that e to the I theta, the exponential form, can be expanded to r cos theta plus I sine theta. We want sine theta. So it's important to recognise that that is exactly the same as that. Right, the problem is we've got extra bits in there. We've got an I in there we don't need. We've got the cos theta we don't need. So we're going to have to see what happens to that. So notice that this is the sum to infinity, same as this is. So that's great. And we know that that is 5 over 5 minus e to the I theta. So I've got this equals this. Right, so what can I do next? Well, I can certainly separate this out. I can separate that to be the 5k dot to that and the e side, and I've noticed that actually some parts of it I do want and some parts I don't. Now the bits I don't want is the real part just there. The bit I do want, which is up here, is the imaginary part. So what I need to do is be able to write this part here in real and imaginary. If I can write this in real and imaginary, then all I will need to do is equate the imaginary parts, because that will give me the answer I require. So how do we write this in real and imaginary? Well, the first thing I'm going to have to do is change that e to the I theta. Now we know that e to the I theta is cos theta plus I sine theta. So the complex conjugate is just a minus version of that, which I know is exactly the same as e to the minus I theta. Okay, that was shown earlier on, and there's the backwards sort of proof of it, that e to the minus I theta is a complex conjugate of that one. Now why that's important is it's going to basically rationalize that or make the bottom real if I multiply by its complex conjugate. So very similar to rationalizing the denominator, this idea of multiplying by that will make the bottom a real number. And if the bottom's a real number, the denominator's a real number, it'll make it very easy to separate it into real and imaginary parts. So let's just check it's true, let's check it works. So if I multiply this by this, notice this is just number 1. It's almost identical to rationalising the denominator, except you're just picking the complex conjugate there. And if I do that, the top part is going to become 25 minus 5e to the I theta. So just check you're happy with that. And the bottom bit is going to get you 26. The reason for that is it's got 5 times 5, 25. That times that is going to get you plus 1, because you've got minus and minus makes it plus. That times that is going to cancel to 1. That's where 26 comes from. But you're also going to get that times 5 and 5 times that, which is where these two parts come from. Okay, doesn't seem very helpful, doesn't seem to cancel out. Right, so we'll have to see what happens with that. This side, all I've done is just pulled an I out. Okay, so I've separated the sigma notation, and you're allowed to do that, as you know from series. Your series work, to separate those two out and just put the I on the front of it. Now that's good, because this is the part I want. That's the part the examiner's asking for. I just need to sort this bit out. Okay, so let's continue playing with this side then, see what I get. So the next stage I'm looking at is knowing that actually e to the I theta plus e to the minus I theta over 2 is just cos theta, or e to the I theta plus e to the minus I theta is 2 cos theta. That's going to help me because this part just here, I can rewrite like that. And the reason why it's helpful is because now look at the bottom. The denominator of that fraction is now real. The top part, which is like that, it's I theta, is got the imaginary bits on. So what can I do? Well, I can simplify this numerator part, and I can get that. We know that from before, just reminding you, 25 minus 5 cos theta plus 5I sine theta. Now, this is, although it looks like a bit of a mess, is very handy because what you can do now is because you've got just a real denominator, you can separate the real and imaginary parts. We can put the 25 minus 5 cos theta, because that's real, over that, plus the I sine theta over that is the imaginary part. So that's what I've separated out. And again, just convince yourself you're happy with that. That plus that is exactly the same as that. Same denominator. So that plus that is where that part comes from. Okay, right. Why have I done that? Because now, if I equate the reals, I would get that series is the same as that. And if I check the imaginaries, I get that part is the same as that, obviously with the i's cancelling out. And in fact, that's exactly what I need to do in this question. So my last stage is equating the imaginary parts, because I've noticed that that's what the examiner is asking for. And so therefore, that must equal 5 sine theta over 26 minus 10 cos theta. Not a very straightforward question. I'm sure if it came up in your exam, you'd have lots of sort of hints and tips to help you through it. But it'd be worth you making sure you practice some of those questions in a minute from your textbook. Okay. So what we're going to look at is another proof. Now this one's a proof that's written in your specification, so you definitely have to have a look at it, but it's not straightforward. So we'll go through it relatively slowly, and you might want to go back over it again and have another look. So I want to prove that cos r theta is the same as this hideous thing just here. Okay, right. So the first thing I'm going to do is expand the summation up to n for cos r theta. And if I do that, I can see that I get cos theta plus cos 2 theta plus cos 3 theta. Now the reason why we're looking at that is because you're checking whether it's an AP or a GP. Am I adding something each time? Well, no, because if I add something to that, it's not going to get to that. Am I multiplying? Again, not really. You're not multiplying by anything to get from there to there, which is the same as from there to there, and so on. Okay, it's not as straightforward as just thinking I'm timesing by cos theta to get cos 2 theta. I'm adding cos theta to get cos 2 theta. It doesn't work like that. So this isn't an AP, and it's also not a GP. And because it's not an arithmetic progression or a geometric progression, I can't use any of the formulas that I know from series sequences. So what I'm going to do is I'm going to have to solve it a different way. And the way I'm going to solve it is by using that same technique we did earlier on of saying, well, I can't do what the exam's asking for just there. But what I do know is how to write it using de Moivre's form theorem and saying that cos r theta plus I sine r theta is written like that. Now, the reason why I do that is because using de Moivre's backwards, I know that is exactly the same as cos theta plus I sine theta to the power r. Now, why that's handy is because now if I write that out, I have got a geometric progression. I'm noticing that I'm multiplying by cos theta plus I sine theta every single time. So I've got an A value of cos theta plus I sine theta, and I've got an R value of cos theta plus I sine theta. Interestingly, both of those are exactly the same. Now, why does that help? Because now I can use the sum formulas to work out what this actually is. And that is the sum of the first n terms of a GP. So that formula is straight from your formula books. And what I can do now is I can fill that part in. I can fill in the A value and I can fill in the R value. So end up with that. Right, now I can do some neatening up, or at least try to do some neatening up. So the first thing I've just done is used the Wiles theorem backwards again, because I know that that's the power n is exactly the same as cos n theta plus I sine n theta, but it was minus for both of it, so that's why we've got to that bit. Right, why does that help? Because I can use my double angle formulas. Now this seems a really weird thing to say because I don't really have any double angles in this. What I've noticed is that in this bit I've got things like n theta over 2. I've got theta over 2. So I'm using double angle formulas, but in a bit of a strange way. I'm using them by going backwards. So I'm saying that if this is true, which it is, that theta value just there, I'm going to change to n theta. Right? Or 2 theta is going to be changed to n theta. So if that's true, if 2 theta is n theta, then that means that theta on its own is n theta over 2. Just convince yourself that that's true. I've rearranged it. So I've taken that to that side, taken this to this side, and I've replaced the 2 theta by n theta. Okay. Right. Also, exactly the same idea with sine. So sine 2 theta could be replaced. If I replace the 2 for n, then I'll get n theta over 2, n theta over 2. So I can replace it like that. And some of those formulas are quite similar to the formulas in your formula book for single angles. Right, why does that help me then? Well, it helps me because I can now replace some of these n thetas, and I'm going to get the sort of thing they're asking for in the formula up here. So let's have a look how that helps me. So the first thing I'm going to do is just replace the parts from our formula. So I can see that I've got cos n theta there, and that's the same as 2 sine n theta. I've also noticed that I've got 1 minus it, so I've just replaced all of that section, that 1 minus cos n theta, for that. The sine n theta is the same as this part just here, so I've wrote it there. Also on the bottom, using the same formula, but n equaling 1, I've replaced the cos and the I sine for that. Okay. Now the reason why we do that, or the reason why I've done it, is because then I've noticed I've got a common multiple in both these parts. In the bottom, I can pull out a 2i sine theta over 2, and on the top I can pull out a 2i sine n theta over 2. I couldn't do that before, but I can do it now. And what I'm noticing is that although I don't see a 2i sine n theta in this section, if I pull that out, I can actually just put an I value inside. So again, just check you're happy with that. That if I did that times that, I get that. If I get that times that, the I times the I will get you plus 1. Minus 1, sorry, but then you've got the minus there, makes it plus 1, which is where that part comes from. Just on the denominator, same idea. That times that gets you that, and that times that, with the i's cancelling to make minus 1, gets you that part. So why does that help us? Because now we can cancel these two parts out. Cancel those two parts out, or not all of it, sorry, because the n theta over 2 and the theta over 2 can't cancel, but the i's can definitely cancel. I will get down to this part just here. Okay. We're going to look at making the denominator real. How do I do that? By multiplying by its complex conjugate. Same as what we did before. So if I multiply it by its complex conjugate, that's going to cancel out this I theta just here. I couldn't do that before because I had the number 1 on the front. Where now I don't. I have this number. It's not a problem with the multiplier, but the 1 minus really messed it up before. So what can I do now? I can bring it in and I can multiply it through. So if I multiply it through, I've only got this times this, but on the bottom I've also got the same. So let's see what we end up with. So on that numerator, we get this massive thing just here. Okay. We get that times that part, we get that bit times that bit, we get that bit times that bit, and so on. So all that top part there is just those two brackets times together. On the bottom, which is quite nice and expected, we've got that times that gets us cos squared theta over 2. That times that is plus and a minus, makes a plus. but also the middle parts cancel each other out because it was to do with the complex conjugate. Now this part, if you haven't noticed, is cos squared x plus sine squared x. So therefore that is just going to equal 1. That's good. So that sorts out the denominator, exactly what we're trying to prove. This top bit though looks nothing like that at the moment. So I'm still left with these two parts. So let's just think what we've got. I'm going to use the addition rules because I'm seeing lots of cos, sine, sines, sine, cos sines floating around. So I can put those two together and get that. And I can also put those two together and get that. Right, so why does that help me? Because finally, after all that work, I can start to consider which bit's real and which bit's imaginary. Before I can do that though, I do have to do a bit more multiplying out on this top right. So if I multiply, leaving the sine n theta over 2 alone, because I know that's going to be my final answer. So I've left that alone. I've just multiplied this bit and this bit together, or this bit and this bit together. So I get this. And then I can use my addition formulas again. Same idea. Cos, sine, sine. And what I end up with is this answer just here. Now finally, I'm in a situation where I can see real times by that will be real over real. Imaginary times by that over that will be imaginary. So I can write it out in two parts, and I can now equate the real and imaginary parts. The real parts are going to tell me that that equals that, which is exactly what I'm trying to prove. You could be asked the same question, but with the sine part, and that would equal that sine part just there. Now that proof that I've just gone through there would not be given to you in the exam for you to just do from scratch. What's quite likely to happen is you to have that as part of another question, or maybe you've got part of the proof and you just have to explain what's going on. Maybe you have to use a double angle, or maybe you just have to do the end bit where you're equating the real and imaginary. So it's important to make sure that you've seen it and you have some understanding of each of the steps, but to be able to just do that proof from scratch is not something you would be expected to do. Alright, so have a go at the exercises on 2D on page 43, making sure that you can at least do most of those exercises on there. Some of the really tough ones, just make sure that you keep asking for help and support with those.